Welcome students back to our online lab adaptation for Chem 10. And in this laboratory activity, we will perform several calorimetry experiments. Now, what is calorimetry? Calorimetry, as you may see the word calor in there, that means something to do with heat, right? So calorimetry is any experiment designed to measure the transfer of heat. The basic premise of a calorimeter is that whatever heat transfer that's occurring, whether that being food or from a hot piece of metal, as we'll be doing in today's experiment, or from ice, something that's colder, not hotter, whatever that transfer of heat results in, it will change the temperature of the water. And since we can measure the change in temperature of water and we know the specific heat of water, we therefore know how much heat is transferred by the equation of Q is equal to M times specific heat times change in temperature. M there was mass, right? Okay, before we get started, I want to also show you the idea of heat transfer. What is heat transfer, right? So I found this cool video that really nicely illustrates. So let's watch it.
Hello, my name is James White, and today we'll be investigating heat transfer. Heat transfer affects our everyday life. For example, it allows our computers to run without burning up. It helps us to design houses that use less energy. It makes cooking food possible. And very importantly, it helps keep us warm or cool, like this radiator. To do this, we'll use a thermal camera. A thermal camera can see the radiation given off by all objects and use it to measure their temperatures. For example, cold objects normally give off less radiation than hot objects, which give off more radiation. The camera records this radiation and creates a picture. The colors in the picture represent temperatures. Hotter temperatures are lighter colors, and colder temperatures are darker colors. In this picture, my hand is warm, but the copper wire below it is cold. Using the lighter and copper wire, we will observe the first type of heat transfer, conduction. I'll show you our simple experiment. Conductive heat transfer occurs when there is a temperature difference between two materials in contact with each other. In this case, the right side of the wire is heated by the lighter. At this point, temperature in the material is very high in one area and cold in other areas. Heat transfers from the high temperature side to the low temperature side. Let's watch as this happens. Over time, the temperature of the material becomes more and more uniform.
All right, so that was the main thing I wanted you to see is this concept called heat transfer. And the main thing in there is that heat is always being transferred from the hotter material to the colder material. As you can see, the heat is being transmitted through this wire from the flame. This whole concept again is heat's always going to be transferred from the hotter or higher temperature to the lower temperature. So whatever you have that's burning in your calorimeter, it will be in higher temperature and it will transfer its energy into the water, which is a colder temperature. Or vice versa, if you have ice in here, then the water that is warmer will transfer its energy into the ice. Okay, and this transfer of energy is conserved. Okay, so what does it mean to be conserved? That means if that piece of object loses, let's say, 1,000 calories of energy, then the water have gained 1,000 calories of energy. There's a conservation there. That means those two values are equal. You can think like this person here is giving $27, and this person have gained $27. Okay, this is called a transfer of money, and heat is the same way. If one loses 27 joules, then the other gained 27 joules. There's a conservation there. Okay, so keep all that in mind as we do this experiment. Open the link that is in your document or copy and paste that link onto a browser. I'm using a Firefox browser. And if you get this message that says your flash is out of date and needs to be updated, go ahead and update your flash if possible. If not, you need to find a browser that will allow this simulation to run. And I will just say run Adobe Flash and allow that. Once you allow it, you will go to this page that will be your simulation. Okay, it will give you directions on to choose your metals in each part or ice in the second part. Okay, you can choose metal X or metal Y. You can change the mass of the metal, change the temperature of the metal, or change the mass of the water or temperature of the water by dragging that bar. Once you have all your settings done, go ahead and click Start. As you click Start, the metal is submerged in the water. Heat transfer is now occurring, and you will see a change in the temperature. Once this propeller stops and the temperature plateaus or does not rise or fall anymore, that is your final temperature that you should record. So I will now do this experiment so that I can show you an example of a known substance. What you're going to do is, when it's your turn is you're going to choose an unknown metal, either X or Y, and you will calculate its specific heat that way. But let's just do it as an example of something that is known. So I'm going to use iron as my metal. Okay, I'm going to make the mass 118, for example, and the temperature of the metal, I'm going to set it at around 100 degrees, and the mass of the water, I'm going to give it to become 85, and the temperature, I'm going to leave it as is. And so once I have all my settings set up, then I can start the experiment. By pressing start, the metal will be lowered and the propeller will start mixing so that there is distribution of that heat in the water. Notice that over time, this water in the calorimeter is going to increase in temperature because heat transfer is occurring. Okay, once the propeller stops, the reaction has stopped, then we will have no more increase also in the temperature of the calorimeter. That means all the heat has been transferred successfully. At this point, this is called thermal equilibrium. Equilibrium means there's no more visible change in terms of temperature. The temperature of the water and the temperature of the metal are now equal to each other and will not be changing. You can see it fluctuate a little bit here, but it's really not, right? It's not changing dramatically. So let's use this example to calculate our specific heat. In this case, the specific heat is known. In your case, when you use unknown metal, this box will be left blank or has a question mark. Okay, so let's go to the analysis section of today's lab. And these are the types of measurements that you will also hopefully have recorded. Your numbers will be different than mine because you have an unknown metal. Mine was a known metal. Okay, right, so as you can see here, you have the measurement of the mass of the metal, which I will abbreviate as M sub M for mass of metal. And I have the initial temperature of the metal. I have the mass of the water, M sub W for water. I have the initial temperature of the water. And then finally, when we add all those things together and they come to thermal equilibrium, the final temperature of the water was also recorded. Now note, remember I said thermal equilibrium means the temperature of the water is equal to the temperature of the metal, right? So this value is also the final temperature of the metal. So we have all those numbers and they will help us solve this problem. So let me walk you through the analysis in your activity today. So the first thing we'll want to calculate is the heat that the water has absorbed. Okay, so to calculate the heat that the water absorbed, remember that heat was transferred to the water, and did it change the temperature of the water? It did. If it changes the water's temperature, then heat is calculated with which equation? Because temperature of the water changed, then the Q, or the heat of the water, is calculated as mc delta T. Okay, remember C here means a specific heat. The lab writes it as SH, I write it as C. So don't get confused with that. Okay, now let's be a little bit more specific here. It's not only just mc delta T, but M of the water, C of the water, and the changed temperature of the water. So you need all those subscripts. Okay, so let's plug that in. First, how do we know the mass of the water in the calorimeter? In this case, it's pretty simple because it's already given to us, right? The mass of the water is there. So that's taken care of. What about the C of the water, the specific heat of the water? Is that a value that we know? It is, right? So C for water is 1.00 calories per gram degrees Celsius. So that we know already. Cool. How about the change in temperature of the water? Now let's calculate that quickly then. Right? The change in temperature of the water is equal to T final minus T initial. Okay, so what is T final? T final of water is, in this case, this value right here, right at the end. You get 31.48 degrees Celsius minus what is the initial temperature of the water? No, that's of the metal. Initial temperature of the water was here. So that's minus 20.00 degrees Celsius. Okay? So delta T is then equal to 11.48 degrees Celsius. Okay, so then now we also know the delta T of the water. So go ahead and plug all those values back in. So QW is equal to the mass, which is 85.0 grams, times specific heat is 1.00 calorie degrees Celsius, and the change in temperature is 11.48 degrees Celsius. Okay. Let's check our unit analysis here. Grams goes away, degrees Celsius goes away, leaving us only calories at the end. Okay, so go ahead and take our calculator again. QW then is equal to what? Okay, that is equal to 975.8 calories. Okay, so let's just keep track here. We have 3 sig figs. 1, 2, 3. So we should only really have 3 sig figs there. But if you record this, 976 calories. Okay, that's the first heat energy absorbed by water calculation. Okay. Okay, now why is that value important? Remember we said that heat transfer is a conserved process. That means whatever you give, the other person received the exact amount, right? So in this case, if water received 976 calories of energy, where is that coming from, right? What's giving water that much calories? It's the metal. So we also know from that relationship that what we call the heat of the metal is equal to the heat of the water. But now there's a little thing you need to add into this is the fact that things that are given or taken have opposite signs, right? If you gain something, then you have a positive sign. If you lost something, it's a negative sign, right? And in this case, it does make sense because then if we plug that value in here, QM is then basically the negative of 975.8 calories, which makes sense because the metal lost the heat, right? The metal lost energy, so it's now negative 975.8 calories. Notice I put the unrounded number because this is not the final answer, so I'm going to use it as unrounded. So our next question, A2, asks us to calculate the specific heat of the metal. Okay, so how will we do that? Let's delete all the subscript. Now we can use an equation, the same equation, but of the metal. Again, why can we use this equation? Because the metal change in temperature, so therefore you can use the MCAT equation. Right, so this is Q of the metal, mass of the metal, specific heat of the metal, and change in temperature of the metal. In question A2, what is it that we are asked to find? We're asked to find the specific heat, correct? And so which variable represents the specific heat? That one, right? Okay, so we have to rearrange this equation so that we can solve for specific heat. To do so, we have to divide both sides by the mass and the change in temperature. What we do on one side, we have to do on the other side. Okay, so rewritten, this equation for specific heat of the metal, you get, okay, so remember that mass goes away, delta T goes away, so on the left-hand side, you have Q sub M divided by M sub M delta T sub M. Okay, the Q sub M we already know, yay, that was up here. The M sub M we also know because that's the mass of the metal right there. So the only thing left we have to worry about is the change in temperature of the metal. So how do we know the change in temperature of the metal? Well, what's the final temperature of the metal? In this case, it is, yes, 31.48. Remember, the final temperature of the water is also the final temperature of the metal because of dynamic thermal equilibrium. Okay, minus the initial temperature of the metal. In this case, it is 108 degrees. So delta Tm is equal to, that gives us negative 76.52. Okay, so now we also know the delta T of the metal. Okay, so yay, now we know that. So plug in all of those things and see what we get. All right, so the Q of M, all right, so let's plug Q of M in, is negative 975.8 calories. The M of M is 118.00 grams. And finally, the delta T is negative 76.52 degrees Celsius. Cool, right? So notice that there's a negative sign here and negative sign there. That makes this a positive number. The specific heat is always going to be a positive number. What's our unit going to be? We got calories, we got grams, and we got degrees Celsius. So our unit is going to be calories per gram degrees Celsius. Nothing cancels out, but we still have to go ahead and do the calculating for that, which is 975.8 divided by 118 equals divided by 76.52 equals. Remember, this number had only 3 sig figs in it. This has 5. This has 4. So the answer again must be 3 sig figs. In this case, I forgot what the answer was. 3 sig figs would be 1, 2, 3. So 0.108 calories per degree Celsius. Okay, so remember we knew this was going to be iron. So let's look up the specific heat for iron. And if we go to our table of specific heat and look up iron, it is 0.108. Ah, perfect. We got it. Exactly. Calories per gram degrees Celsius. So that's what you're going to do for your own unknown metal. And once you find the specific heat for your unknown metal, you can match it up to find what is the identity of your unknown metal. Now in part B, you're going to do a very similar process because again, we're using a calorimetry to study heat transfer. But in this case, we do not have a metal, but we have ice that's melted. And in melting that ice, there is a heat transfer. In the first case, the metal was hot, and so it transfers energy to the water in the calorimeter. In the second case, though, the ice is colder than the water in the calorimeter. So the heat transfer is not from the substance into the water of the calorimeter, but from the heat is transferred from the water into the substance in the form of ice and melting it essentially. Okay, but again, since it is heat transfer, we can still use the equation that the heat of the water is equal to the heat of the ice. Again, it is opposite of each other because one is giving and one's receiving. Now, to help you out a little bit, and I won't go through the whole problem here because the process is very similar to the first case, but there is one difference here that I want to point out. But first, what is QW? The equation going to be for QW. We have to first solve QW, right? Well, QW is, again, is there a change in temperature of the water in the calorimeter? There is, so which equation do we use? The MCAT. Very good. Okay, once you get that, you will get this value. And once you get that value, you can plug it into this Q of ice in order to find the heat of fusion of water. Okay, now, what is Q of ice though? Do we use MCAT this time? In this process, did the ice change its temperature? No, right? It's just melted. And melting is a phase change. Right? So if it's a phase change, what equation are we going to use? M heat times the heat of fusion. Okay? And indeed, this is a value that you will be looking for. Rearranging this equation, the heat of fusion is equal to the heat of the ice divided by the mass of the ice. Okay? Remember that this value you can plug in from this relationship, and this relationship was derived from that equation. And the mass of the ice is something that is already determined from your simulation. Okay, well, good luck and have more practice. If you want, there's more practice at the end of your lab manual, and so you can take a look at that and see for yourself.